Hello everyone, my name is Daniel. I am a PhD student at the University of Kent, which is in the south of England, and I work on the research programming language Granule. So just for my own interest, is there anyone in here who's already heard of Granule? Great. So there's a couple of you, which is good to see. There's also a lot of you that are going to learn something today, which is really good as well. So this is called A Hitchhiker's Guide to Linearity. That's linearity as in the programming language concept that's based on Girard's linear logic. The reason this is a hitchhiker's guide is that linearity comes with a lot of different names in a lot of different forms, and it's not always clear how these different but similar concepts relate to each other. So you might have heard of linear types. If you're a Haskell person, for example, you've seen the new linear types extension they've come out with. You might have heard of uniqueness types from way back in the Clean programming language, although there's a few modern languages following Clean's footsteps. You might have heard of ownership and borrowing systems, most famously in Rust, but also other languages like Swift, for example. These are somehow based on linear logic, but not clear exactly which concepts come from the logic, which concepts are added in. If you're really up on your PL research literature, you might even have heard of quantitative types, as in Idris, or graded types, which Granule is especially known for. So today we're going to bring all these together. We're going to go through a quick tour through all of these ideas. We're going to look at the similarities, the differences, and we're going to think a bit about, if you have an application in mind, which of these ideas should I be using for that application? So hopefully that sounds fun. First of all, we need to think about what it is that all of these separate but similar concepts have in common, right? And the idea is that we want to use our type systems to think not just about what kind of data we're working with, like is this thing an integer, is this thing a string, but also to think about how that data we're working with is going to behave. And this is a really important idea, right? Some data, it doesn't matter how we use. We can take it, we can do whatever we want with it, and we don't have to worry about linear typing or any of that kind of thing. But some data represents that we have access to some kind of resource, and so we have to use it in a resourceful way. So some examples of that are we can't always take a piece of data and infinitely copy it as many times as we like. We can't always take a piece of data and throw it away without following some procedure first to do that safely. And we can't always take data and mutate it directly in memory if, for example, someone else might have access to it at the same time. So these are all things that sometimes it's totally fine to do, but we can't be allowed to do them universally. And so that's where these type system concepts come in. Now, the first thing we're going to look at is linear types, which are probably the closest, most related to the original logic, and so they seem like a good place to start. Now, there's an analogy that I always like to use when I'm introducing linear types for the first time, just so that people understand the very basics. The analogy that I like to use is that linear types behave like a delicious piece of cake. Why do they behave like cake? Well, if you have a cake, unfortunately, we live in a disappointing world, so once you've eaten it, you can't eat it again. It's gone. But if you have a cake, then you do have to eat it. Otherwise, your friend who baked you the cake might be very disappointed. That's how this idea might look in a functional programming language with linear types, such as Haskell. Now, linear types in Haskell are an extension, so we have to enable this pragma here, linear types. Other than that, this looks very similar to an ordinary Haskell program. The one difference that stands out, which I've highlighted in blue, is this function arrow here. It's kind of shaped like a lollipop rather than an arrow. So what this tells you is that the argument to that function, so the thing that appears on the left-hand side of this arrow, with this cake value here, that has to be used in a linear way. So it follows these rules that we've mentioned above. We can't just copy it and use it more than once, but we have to use it at least once. We can't just throw it away. So what's going on the right-hand side of this function is, first we eat our cake, which makes us happy, but then we also have our cake, which means that we have a cake. Not very interesting. But we're trying to have our cake and eat it too, and we shouldn't be allowed to do this in a linear type system, because on the right-hand side, we've used this value of type cake twice, and it's a linear value, so this has to be disallowed. Hopefully that makes sense so far. That's just the basics. We're going to do some more practical examples later on. Before that, I want to show you how these linearity concepts translate into our language Granule, because going forwards, Granule is the language we're going to be working in a lot. So the main difference from Haskell, okay, there are some minor superficial differences, like we use a single colon for the type signature rather than two. That doesn't really matter. The main difference, though, is that rather than being an extension built on top of an existing language, linear types in Granule are the default. Granule has a linear base, which means if I just define some regular value of type cake, that value is automatically going to have to be used linearly. So for exactly the same reason as on the previous slide, this function would not compile in Granule. You would get a type error, because on the right-hand side, we've used the linear value of type cake twice, and we're not allowed to do so. Now, you might be thinking, okay, well, if your values are linear by default, how on earth am I ever going to get anything done right in programs in this language? It's going to be a massive pain. And you would be right to think so. So linear logic itself gives us a way to kind of escape from the linear world and work with things that don't always have to be linear. And the way that that works is it's called the bang modality. So highlighted in blue up here in the type signature, you can see that the cake is now preceded by this exclamation mark thing. A modality is this kind of prefix constructor that comes before the type, and it changes how the type behaves. And in this case, we have this exclamation mark as the modality. And what that means is it wraps a value inside, and the value that's wrapped inside can be used in a nonlinear way. So we are allowed to copy it, we are allowed to discard it, and so on. So if we look at what's going on inside this function, we take the value on the left-hand side, which I've called lots, because you can think of it as representing a lot of cake, possibly even an infinite amount, who knows. On the right-hand side, we pull the value called cake outside of the bang modality so that we can use it. And then, just like before, we eat our cake, which makes us happy, and we have our cake, which means we have a cake. But here, we don't just want to have a cake, we want to preserve the fact that we have a lot of cake. We want to carry on using it in a nonlinear way in the future. So we have to wrap that back up inside the bang modality. Now, the syntax we use for that in Granule is these kind of square brackets that you see in the function here. That might seem like quite a bizarre choice at this point. We will explain that later on, but just remember that what that's doing is wrapping back up inside the modality.
Could you just written lots, eat cake, comma lots? After all, lots has type back cake.
Yes, I think that would be fine. I just wanted to demonstrate the syntax here, but yes, that makes sense to me. So this is kind of a fun toy example. Hopefully that's gotten across the basic ideas, but let's have a look at a slightly more practical example where we do some more interesting things. So let's look at the case of a file handle, which is the kind of thing that we have to use in a linear way. We can't copy file handles, we can't discard file handles, okay? So here's some Granule code. Now, there's a bit more going on here. So if you look at the type signature, you'll see this IO thing that appears in the type. So what this is it's an effect. Effects in Granule are I could give a whole talk on those in themselves, but for now, if you just think of, in this example, we're basically working in the IO monad in the Haskell style, you won't go too far wrong. So on the first line of this function, after the let, what happens is we open a new file handle called H, and we are reading some particular value here. It's an arbitrary value. It doesn't matter which one, as long as we know where it is. On the next line, we read a single character from that file. So that character comes out as C on the left-hand side here, and we also have the handle again, which is now called H prime. And then on the final line, we return the character value from the function. So that's the C. We wrap it back up inside IO. So that's what the pure is doing. But there is a problem with this function somewhere. Has anyone spotted it already? I'm sure someone has.
What happened to H prime?
Exactly. So the problem that's happened here is, if you know anything about file handles or anything about linear types, the problem is that we haven't closed our handle, right? And the nice thing about a linear type system is, even if you didn't think, oh, I need to close this handle before I'm done with it, if you accidentally made this mistake, the linear type system would catch that for you, because this new handle that we ended up with on this line, this H prime, we never used it, right? And as I said before, every value in this system has to be used in a linear way. So because we didn't use it, we would get a linear type error at that point. So hopefully that makes sense. Linear types are letting us catch an additional kind of error that we wouldn't have been able to catch before. And this doesn't solve every problem you can cause with file handles. There's a lot of trouble you can get into with file handles. So we haven't made them harmless, but I think it's safe to say that we've made them mostly harmless.
Can you put your H in square brackets to make lots of handles?
No, and you can't.
Why not? What stops you?
There are some things that you cannot wrap up inside modalities in Granule. So specific kinds of resource. We call them resource allocators, so there's kind of a particular restriction here. I might come back to this at the end because there's more I could say, but I'll leave it at that for now. So now let's have a look at a slightly different perspective on linearity. So let's look at the idea of uniqueness types, which, as I mentioned, were made popular by the clean programming language. Now, these are similar to linear types in some ways, but there are some important differences that we will see. Now, again, of course, we need some kind of analogy to help us understand uniqueness types better, just like with linear types. The analogy that I'm going to choose here is that rather than cake, uniqueness types are like a fresh cup of coffee. Why is that the case? Well, as I said, the point of uniqueness types is to ensure that there's a single reference that exists to a value, okay? So the way that that is like a cup of coffee is, if we pour a cup of coffee for ourselves, then we know that that cup of coffee is fresh, right? We know it hasn't been touched by anyone else. No one else has had access, so we can guarantee that. Now, we can sip our coffee as much as we like. We can share it around with other people if we want to. But what we can't do is we can't go sharing it with other people and telling them that it's still fresh. That would be a terrible thing to do. I'm sure no one would do that kind of thing. So this is how that looks in the clean programming language. Now, again, we have quite Haskell-ish syntax here, so hopefully we're not going to go too far off the rails worrying about syntax. But the one difference we have here is that now we have this star that appears in the type signatures. This star just tells us that this value has a unique type, and so it has to be used in this unique kind of way. So what's going on here is we have a cup of coffee over here, which we're saying is fresh, it's unique. Over here, we drink our coffee, which makes us awake, but we keep our coffee to carry on drinking from it later. Now, what's wrong with this function, and there is something wrong with this function, clean would give us a uniqueness error here, is that on this right-hand side, we've created another reference to the cup of coffee here when we drank from it. So on this right-hand side, where we're saying the coffee is still unique, this isn't true, because now two references to the coffee exist. So we can't keep this uniqueness guarantee here. Okay, hopefully that makes sense.
It doesn't sound different to what you said before about cake.
True.
It sounds the same.
So let's go on to the next slide.
Okay.
All right, carry on.
Okay, what's on the next slide?
That's a great question. Let's find out. So you might think from these two examples that linear types and uniqueness types are not that different, right? Because I've written those two pieces of code and they basically show the same property there, right? So it's not entirely clear at the moment what the difference is here. So let's have a quick look at what the literature has to say about the difference between these two things. If we look at advanced topics in types and programming languages, this is a great book, great reference. It doesn't say very much about uniqueness types. All it says is that uniqueness types are a variant of linear types. Okay, the implication there is they're kind of similar, but there's maybe some crucial difference that we need to know about. If we look at the linear Haskell paper, of which some of the authors are in the audience, this goes into a bit more depth. So this says that linear types and uniqueness types are at their core dual. And then there's some explanation of what this means about the difference between people who call the function and where the function is calling and so on. I don't think this explanation is maybe the most intuitive, the easiest to grasp the first time you think about these things. So let me tell you the intuitive explanation that makes the most sense to me about what the difference is between these two properties, what different property is holding here. What uniqueness types tell us is they tell us something about what has happened to a value in the past. They give us a guarantee that a value has never been duplicated. We can't have more than one reference to the value, and the reason for that is because no other references have been created before. Linear types, on the other hand, don't tell us anything about what's happened in the past, because remember, we have the bang modality. Something could have come from the bang modality, so we don't know how many references exist in the world, right? But what they do tell us is we have a restriction in the future. Linear types tell us this value that we have, if it has linear type, is never going to be duplicated or discarded. So this is kind of the main difference here. Now, while we digest that, let's take a little bit of a detour and say a little bit about the history of these two concepts, just to kind of ground ourselves and think about where these two things came from. So I'm going to list some papers here, and I'm going to put them on a spectrum from theory to practice. I'm not going to list every paper that has ever been written about these two ideas, because we would be here for probably a few months. I'm just going to list a few so that we get the idea of how these things developed. So, of course, linearity, as I mentioned towards the beginning, all started from linear logic in 1987. So it was originally this kind of theoretical concept that a logician came up with to do logical things with. But it wasn't long after that, of course, until programming language people like Philip Wadler, among others, started to think, this linear logic seems very useful for programming languages because there are a lot of things that need to behave in this kind of linear way. So what if we turn this into a type system? There were plenty of papers written about this at the time. But I think it's fair to say that it took quite a long time after that for these to really see any kind of mainstream adoption. So before this paper, there were certainly implementations of linear types in more experimental, more research-based settings. But I think it would be reasonable to say this is the first example of a time when linear types have been incorporated into a sort of mainstream, depending on how you think of Haskell, programming language that people can really play around with and use while still being able to use a language that they're familiar with, right? So linear types kind of went from theory to practice later on, whereas uniqueness types have kind of the opposite history. So the way uniqueness types started off were as a practical tool to solve a practical problem. And that's this problem of I want to make sure that these values only have a single reference to them, in the clean programming language in particular. So this paper was the first paper that really talked about uniqueness types back in 1994 by the clean programming language people, and it was all about their implementation and how it worked. And then it took quite some time after that before people started thinking about, okay, if linear types come from linear logic, these uniqueness types seem quite similar. Can I define a logic that will represent uniqueness types, and how can I sort of connect these? And then once that was done, there were plenty of papers by, for example, Idris, among others, which sort of thought about, okay, how can I make this more practical? What can I add into the system, and so on. So kind of opposite histories here, where linearity went from theory to practice, the uniqueness types went on a spectrum more sort of from practice to later a theory was developed. And so this is why it's only kind of recently where we can start thinking about, okay, I have linearity, I have uniqueness. How can I understand the relationship between these two things? How can we bring them together? So in order to do that, probably the best place to start is to start thinking about this uniqueness logic that I've just mentioned, right? Because if we can understand what the differences between linear logic and uniqueness logic are, that will give us a great starting point to start thinking about, okay, what are the differences between the type systems, okay? Now, uniqueness logic to start with seems quite similar to linear logic. So the structural rules, which are the particular logical rules that let us have this behavior of copying things and throwing things away, they're called contraction and weakening. Those are restricted just like in linear logic. So for arbitrary values, we can't just copy them, we can't just throw them away. Also, we have a modality, which in uniqueness logic happens to be called circle rather than bang. And that modality allows us to discard and duplicate things that are wrapped inside it, just like the bang modality. So far, these two things seem very similar. And in fact, if all you have is these two separate worlds, unrestricted things and linear things, where some things can be duplicated, some things can't, and there's no interaction between them, then there is no difference between a linear type system and a uniqueness type system. This kind of type is called steadfast types, which was coined by Philip Wadler back in one of his original linear type papers. The difference comes about when we start trying to move from nonlinear things to linear things, or the other way around. So changing unrestricted things and restricted things into one another. Now in linear logic, what we can do is, as you've seen on previous slides, we can take something that's wrapped inside the bang modality, pull it out, and carry on using that thing as a linear thing which is now restricted. Whereas in uniqueness logic, things go in the other direction, right? So I can have a thing that I know to be unique. I know I have the only reference to that thing. I can say, okay, I don't care about this thing being unique anymore, so I'm going to share it around and make as many copies as I want, but I can no longer now pretend that that thing is unique. I have to add this non-uniqueness modality to be able to say, okay, this thing isn't unique anymore. Okay? So if you're familiar with the concept of a monad, for example, in Haskell, or just generally in category theory or anything like that, this non-uniqueness modality from uniqueness logic is exactly a monad. The important thing about that here is just that it gives us this behavior where you can put something inside the monad, but then you can't pull it back out again. On the other hand, it's well-known fact that the bang modality from linear logic is a comonad, which is kind of the opposite or dual to a monad. It gives us this behavior where we can pull something out of the comonad, but then we can't put it back in. So this is kind of where my research began a few years ago, thinking about, okay, we have uniqueness logic, we have linear logic, uniqueness types and linear types. How can we put these things together and have things that behave in unique ways and linear ways all in the same system? And the crucial insight for doing this is right here on this slide, right? Because what we can see from this slide is that there are really only 3 states that it's possible for a value to be in such a unified system. We can have things that are unique. These things guarantee that they've never come from something that was not restricted, so we know we have the only reference to them. They've never been duplicated in the past. We have unrestricted or nonlinear or non-unique things, which the word we use for that is Cartesian for mathematical reasons that we won't go into. These things are not restricted at all, and we don't have any guarantees about them. So they could have been duplicated. We might be going to duplicate them. We just don't know anything about them. They're just standard values, basically. And finally, we have linear values, which we don't know anything about where they came from in the past, because they could have come from something that was unrestricted. But what we do know is that they're never going to be possible to duplicate or discard in the future. So 3 kinds of values: unique, Cartesian, and linear. Press the wrong button. So putting all of this together, how do we develop a type system that has all these kinds of things in? Well, it's basically exactly as I've just showed you. We have 3 different kinds of values. We have linear values as the base, just like in Granule and just like in linear logic. So these don't have any modality that comes with them. We have Cartesian values with this comonadic bang modality, again, just like linear logic. And we introduce an additional modality for unique values. The syntax we use for this is the star, which is basically lifted from clean, just so that it's familiar syntax, doesn't confuse people reading about clean. And the way that we can move in between values of these 3 different states is exactly as you would probably expect given the previous slide. We can go from Cartesian to linear, which is often called dereliction in linear logic papers. We can pull something out of that bang modality and make it linear. We can go from unique to Cartesian, which we call sharing, because that's basically what you're doing. You're saying, I have the only reference to this value. I'm now going to share it so that we can create more, but it's not unique anymore. So you can go from unique to Cartesian to linear, but not backwards in the other direction. So, well, let me go back for a second, actually. What this kind of begs the question of is, okay, if we know that the bang modality is a co-monad here, which we haven't changed anything about the way that it works, how exactly does this new star modality behave? Because it's not quite the same as that modality we saw from uniqueness logic, the little circle modality. It behaves slightly differently because we're going in a different direction here. So what is the behavior of this? Now, there are two main rules for the behavior of this modality, and those are implemented as primitives in Granule when you're playing around with this. So I'm going to show you the Granule type signatures of those rules, those primitives now. So the first one is called share. Now, there's a new piece of syntax here, which is this for all in the type signature. This is just how we do polymorphism in Granule. We require people to be a bit more explicit than they have to be in Haskell. So this just says that for any type A, then we can take a unique value of type A and turn that into a Cartesian value of type A. So this is exactly what you would have seen on the previous slide. This just represents that sharing behavior. We also have a slightly more complicated primitive, which is called clone. So the way this works is, say that I have a function, this middle argument to the clone here, which requires a unique input of type A and returns some unrestricted thing of type B. But I don't have a unique thing of type A, I only have an unrestricted thing of type A, so it seems like I can't do this. The way that we can make this work is we can take our unrestricted A, we can make a deep copy of that thing, so we make another thing that is exactly the same in whatever details, but it's a separate instance of that thing. And now, because we've made that deep copy, we know we have the only reference to that copy, so it's safe to say that it's unique. And that's why we can now pass that thing into this function and get the unrestricted B out. So these are the kind of two key rules here for uniqueness, share and clone.
Why did you say bang B rather than just B on the output? I mean, that seems like a more specialized type. If I just said B, then...
Yeah, I suppose it could work with B. I mean, you can make this thing work with a thing of type B anyway, because then... Okay, no, I guess you can't, but yeah.
Maybe I should ask, can I instantiate a typo with bang something?
I think you should be able to do that, yeah.
So then it would just become more polymorphic if I remove the bangs on the beats. Because I could always instantiate.
I think you might be right, yeah. I think there might be a reason. Like, I think there's something that can go wrong if you don't have this non-linearity on the output, but I...
With bang things. Okay, anyway,
Yeah. If I get to the end and I've remembered why it goes wrong, then I will let you know why it goes wrong, definitely. But for now, so this kind of gives us a clue as to what sort of algebraic structure we're looking at here. So if you're looking at these rules and you've seen a lot of Haskell, you might think these look quite similar to the typing rules for a monad, and you would be right. So just to remind you of what those rules look like, if we have a monad in Haskell, these are the things that we can do with it. We can return a value into the monad, so that lets us take something of type A and put it into the monad. And we also have the bind function, which lets us do this, basically, so binding a function over the monad. Now, these are quite similar to the rules that we've got above, so they almost make it look like that bang is acting as a monad here, but not quite. And the reason why it's not quite is because of the presence of this additional star modality here in the two primitives at the top. So we have something almost a monad, but not quite there. Now, there is a name for this particular algebraic structure that's going on here. What we say is that the bang modality is acting as a monad relative to the presence of this additional star modality here in these primitives. Or in other words, the bang modality is acting as a relative monad of a star. So there is monadic behavior going on here, we just have to account for this extra modality, and so we end up with a relative monad. And for people who really know about these things, there are some extra properties that a relative monad does have to follow, and this thing does indeed follow them. So it's nice to know that we've uncovered some kind of deeper structure here in the way this thing behaves, rather than just coming up with an arbitrary modality with arbitrary rules. But the theory looks nice, but how does this all work in practice? Can I actually play around with this and write code that uses unique things and linear things? Well, yes, you can, and if you would like to, then I strongly encourage you to do so. You can download the Granule compiler from the Granule website. I haven't done any live coding in this talk, one, because I don't have time, and two, because this is not my laptop. But I don't really need to, because you can run all of these examples for yourself and check that they work. So how does this work in Granule? Well, we already know it has a linear base, as we've seen. We already know it has the bang modality, which is what we call a co-effect, another fancy word, but if you know about effects, those are when a program has an effect on its context, the context that it's running in. So for example, if it prints out something to I/O, that is an effect. A co-effect then, on the other hand, is when a program depends on its context. So the context is having some effect on the program and how it runs. So these are kind of dual concepts here. Now, in addition to those two flavors of modality, effects and co-effects, we had a third flavor, which is for things that behave like this star, that behave like uniqueness. We call them guarantees because what they're trying to do is guarantee that some property holds in the past rather than the future, as co-effects do. So here's an example of some code that makes use of all of these things. Now, this is basically the same as the clean example that we saw earlier on. There's not much new going on, except that we use linear types in here as well. So on the left-hand side, we have the fresh cup of coffee just like we had before. On the right-hand side, we drink from our cup of coffee to make ourselves awake, and we keep our cup of coffee to drink from and share around later. But the difference between this example and the one that we had before is that now we're no longer pretending that our coffee is still unique on the right-hand side. We're using the share function that I've shown you to turn that into an unrestricted cup of coffee. So we can share it as much as we want. We just can't say that it's still unique, that it's still fresh. So just a simple example making use of all of those things. Hopefully that makes sense. But just like we did before with file handles, I want to go through a slightly more practical example of how uniqueness types look in Granule. And I'm going to do this with arrays that we can mutate in place. So this is one of the advantages of uniqueness types, that if I have the only reference to something, I can mutate it safely and it'll be fine. So here's some simple, hopefully, code. It's not too far different from what we were doing with the file handle earlier on. So on the first line, we're creating a new array of size 3. So here's an illustration of how that looks. We end up with this new array in memory. It has 3 cells indexed by 0, 1, and 2, and we initialize them all with the float 0.0. And we have a reference to that, which is called A. On the second line, we're going to write to that array. So we're writing to A, we're writing into index 1, and we are writing the float 4.2. And when we do this, because we have the only reference to that array, it's safe to do this in place in memory, just as a simple array mutation, like so. So we've mutated that cell in memory that is indexed by 1, and we've ended up with the result 4.2 in that cell. So when we get to the last line of this function where we read from the array, we end up reading from the index 1, so we get the result 4.2, and this all works fine. Hopefully that made sense, but just to sort of demonstrate why this is having any change on what happens, like why does this have any benefit, I want to contrast this to what happens with regular immutable functional arrays. So this is basically the same piece of code, but instead of using a unique array, I'm using a standard float array, and I'm using these immutable versions of the array primitives. So what happens here is that on the first line, we still create a new array in memory of size 3. Exactly the same thing happens as before. But when we try and write to this array, because it's a standard functional array that we don't know we have the only reference to, we can't just destructively mutate it in memory because someone else could be reading from it, for example. So we have to create a whole copy of the array, and this version has 4.2 at index 1 rather than the 0.0, which the original version had. So then when we read from it, we're going to get the same result because we're still reading from this updated cell, so we still get 4.2 in the end. But this is going to be less efficient, especially if you imagine we did a bunch of array writes, like 1,000 or something. Then we would end up with a lot of copies of this array. But the nice part about uniqueness types is we don't just have to stick to one of these approaches. We can mix and match, right? So let's say that I need this function to return an immutable value for whatever reason. Maybe my caller just needs one of those because they're going to have some kind of sharing behavior. But I want to make this function itself more efficient because I know that throughout this function I can guarantee that I only have the unique reference that exists to that array. So we can do that, right? Because I can write the first 2 lines of this function in the unique style we saw 2 slides back, where we create a new unique array and we write to that array destructively. Then we can share that array and enjoy. We don't have to worry about uniqueness after this point. Everything's going to be fine because we have an immutable array at the end. So then when we read from it here, this is just an example. You can imagine more complicated behavior happening beyond this point. We're still going to get the same result, right? So we can kind of mix and match those 2 styles where we need to. Hopefully it's kind of clear from that what advantages these unique arrays offer, but just to kind of show that in a bit more detail, it's safe to mutate them in place, so we get some performance benefits from doing that because we don't have to make a bunch of copies of the array. So here are some sort of statistics, some graphs from an experiment we ran when I was writing the first paper about these things a couple of years ago. This is just from one particular experiment that involved doing a bunch of writes to arrays. So this isn't the be-all and end-all saying uniqueness types are better for everything. I just want to demonstrate where exactly this benefit comes from. So here the blue line is the standard immutable arrays, and the pink line is the unique mutable ones. So you can see that the overall runtime of this particular code that we ran went down. The reason for that, if you look at this second graph, is almost all of that time was saved during garbage collection, right? So you can imagine if we had 1,000 writes here, in the immutable case, we'd be making 1,000 copies of that array, and at some point, all of those copies have to be cleaned up by the garbage collector. Whereas with the unique case, where we're just mutating one array in memory, then we don't have to do garbage collection at all, because that's the only copies of that reference that exists. When we deallocate that array at the end, then we can get rid of that array then. We don't have to worry about cleaning all these copies up along the way. So that's cool, and hopefully it's given you a bit of a better understanding of linear types and uniqueness types and how exactly these two things interact with one another. Let's start thinking about some of the kind of more complicated, more precise type systems that we can build on top of those that let us express more properties. For example, the graded types that Granule is known for among people who have heard of it. So if we start from linear logic, which has this bang modality, the bang modality just tells us that, okay, this thing has nonlinear usage. We can use this thing any number of times. But that doesn't let us be very precise in what properties we want to express about these things, right? We either have a linear thing, which is very restricted. We have to use that thing exactly one time. Or we have a bang thing, which is not restricted at all. We have no idea how many times that thing is going to be used. So this doesn't let us be very, very particular about how we're using things. So not long after linear logic was developed, bounded linear logic was developed, also by Girard, among some other people. And this lets us, instead of just having one bang modality, have a whole family of bang modalities which have this kind of annotation on them, giving us a bit more information. Now this R here is usually a natural number, sometimes a polynomial in some bounded linear logic settings. We're going to just go with a natural number for this talk to keep it simple. And that natural number gives you an upper bound on how this thing is going to be used. So for example, rather than just linear things and nonlinear things, I can now say, okay, I have something that has to be used exactly once, or I have something that has to be used at most twice, at most 3 times, and so on, up as high as we want, right? So beyond that, this was later generalized further by kind of a bunch of people all at the same time thinking about how can I build up systems on top of bounded linear logic, right? So what graded types allow us to do is that instead of having this bang modality, we have a box modality, and the grade now is not just a natural number, but it can be drawn from any preordered semiring. So this is just some mathematical structure of which natural numbers are one example, but of which we also have many other examples. So there are a lot more different kinds of information that we can put into our types beyond just like, how many times is this thing going to be used. So I'm going to show you some examples of this in a second so you can see how this works. Just a quick note before I do that. This box followed by R followed by the type A is how this is written in the theory. In the Granule implementation, this exact same concept is instead written the type A followed by square brackets with the R as the grade inside the box. So these are representing exactly the same idea. I just don't want you to get confused by the slightly different syntax. Okay? So graded model types in action. The first semiring that is interesting, and it's the semiring that you see in kind of every graded type system, so that includes Granule, but also some others, is this kind of 0, 1, many semiring, which is sometimes called non-one-tons, thanks to Conor McBride. So the way this works is we have 3 grades that we can use. 0, that means this thing is not going to be used at all. 1, that means this thing is going to be used exactly 1 time, so it's linear. And many, which means this thing could be used any amount of times. So how does this work? Well, you may notice that the way I describe many then sounds very similar to the way that I described how the bang modality works. So this is the example that we had before, where I can take a huge amount of cake on the left-hand side, eat 1 piece of cake, and then I still have a huge amount of cake left over to eat, right? Now, kind of the secret about how Granule is implemented here is that we don't have the bang modality as a first-class thing. It's actually just a special case of this graded box modality, right? So this is just another way of writing the same program where the cake is graded by this grade many, which means I can use this thing as many times as I want. And this isn't kind of unique to Granule. So also other graded type systems, like for example, Idris, uses this semiring, so you can grade things with 0, 1, and many in Idris 2's quantitative type system, and That's really cool. Also, linear Haskell, which might be slightly surprising, is kind of secretly a graded type system under the hood. So they put their grades on the function errors. So we saw earlier on we had the lollipop error. That's actually an error graded by 1. And the regular function error from Haskell is really a function error graded by many. The user can't use the 0 grade in linear Haskell at the moment, but it does kind of exist in the theory to make everything work out. But this isn't the only semmering that we can use. So there are some other structures that we can play around with. One example of that is exact usage. So as we said before, we can use natural numbers as a grading. So here's a more specific example than that. We can say on the left-hand side, I have exactly 2 pieces of cake. On the right-hand side, I eat one of those pieces of cake. How many do I have left? This sounds like the kind of questions I was asked in primary school. The answer is I have 1 piece of cake left if I've eaten one, right? But the nice part about this, and the nice part about the way graded types work is, I don't have to be this specific here. I can make this more general. I can use polymorphism over the choice of grade here. So I can say for any natural number n, if I started with n plus 1 cakes on the left-hand side, and on the right-hand side I eat exactly 1 of those pieces of cake, then remaining, I'm going to have n pieces of cake left, right? So we're subtracting 1 there, but it lets us be polymorphic over that, and we can now use this for any number, except for if we had 0 here, because then there isn't any value of n that satisfies this here, right? One more example I want to give you is the idea of intervals. So this example is slightly more complicated, not too much, but let's go through it sort of step by step. Here, the first input to this function is a maybe value, just a standard maybe data type, or you might know it as option in other languages. So we either get nothing, so we don't get a cake as the input, or we do get a cake as the input, which is just constructed here. So then the second value, the second input, is going to be our default value. That's the default cake we're going to eat if we don't get any. Maybe it doesn't taste as nice or something, I don't know. But notice then on the right-hand side, we wouldn't be able to represent this function if we were using the exact usage semmering. And that's because these have different usages on each line of the function, right? On the top line, I use this value default 1 time, and on the bottom line, I use it 0 times. But what lets us write this function is this grade here, which comes from the interval semmering. So what this interval from 0 to 1 means is I can use that value any number of times within that interval. So since on the top line I use it 1 time, and on the bottom line I use it 0 times, everything works out fine. And some of you might know this concept of a thing that I can use once or throw it away. This kind of maps onto the concept of an affine type that you might have heard of. So that's yet another linear types buzzword for you to learn today. Affine types are like linear types, but you are allowed to throw them away. You're just not allowed to duplicate them. And we can represent that here using this grade. So that's quite cool. Yes, so one thing that you might wonder is, okay, if you can do all of these same things using the same machinery that you use to do this 0-1 many semmering up at the top, then why shouldn't we be able to add these semmerings into Idris and linear Haskell and other similar graded type systems without doing very much work? And the answer, we think, is it probably wouldn't take that much work. So given that people who work on these things are in the audience, I'm contractually obliged to say there are a lot of people on the Granule project who want to work on this kind of thing, of getting these things out there. So get in touch, and it'll be fun to work on that stuff. But for now, we haven't got much time, so let's move on to the idea of ownership, which is another way to build upon this idea of linearity, but adding more kind of complicated things to it. So obviously the most famous ownership system is Rust, but others are available. And there are many papers that try and model a Rust type system. All of these papers have one thing in common, which is that their type systems are immensely complicated, because Rust's type system is very complicated, right? We're not going to think about all the implementational details of Rust today. We're just going to go over the basic idea of ownership and how it links to what we talked about. So the model of ownership we're going to use here comes from the paper Oxide, The Essence of Rust, which was not written by me. It was written by Aaron Weiss and some other people. They have a really good model for thinking about this, and their model is that ownership can be thought of as a system of basically capabilities, right? So what that means is we have values. Here are 2 examples, X and Y, color-coded for your convenience. And each of those values comes along with a capability which tells us how exactly we're allowed to use that thing, right? So if you have the full capability, like we do here, that means you are the unique owner of that value, and so you can use it however you want. You can write to it, you can read from it, and so on. Now, this kind of system of modeling uniqueness by thinking about, okay, I have the whole capability to that thing, so I can use it in a unique way, is becoming kind of more popular recently. You should look at the paper Linearly Qualified Types, which is by the linear Haskell sort of team of people, because they're thinking about being able to represent uniqueness types in their system in this way. But the interesting property for our purposes here is that we can split these capabilities up into pieces. And if we do that, that gives us a way to understand borrowing. Here's an example. So if I have x and I create another reference which borrows that value x, we can split this capability up into two pieces. So now we have part of the capability in each side, but we don't have the full thing. So what that means is we don't have unique access to the value, so we can't mutate it safely. But we do have access to the value, so we can read from it, and that is totally fine. Another example is if we create what's called a mutable borrower to the value. So here we create one to y. Now we need to pass the whole capability along to tell the mutable borrower, okay, it's safe to mutate that value. But then this original owner is left with none of the capability. So the original owner doesn't have access to the value at all until it gets that capability back and regains ownership. Here's just a few simple examples of Rust code, very, very small, I promise, just to kind of make these ideas make more sense in your brain. So the examples we're going to use all focus on this simple data structure that represents a color. So it has three components, red, green, and blue. We create a value called Granule, and this just happens to be the nice light blue shade of the Granule logo. I'm not advertising in this talk, I promise. And so here's some examples. So here if we create two references to the Granule value, both immutable borrowers, then that's totally fine, because these are both allowed to read from the value, but not to write to it safely. Whereas if we had tried to create two mutable borrowers, this wouldn't have been allowed, because we can't have two references mutating that value at the same time. This can lead to problems, as we've mentioned. In fact, even if we tried to create one mutable borrower and one immutable borrower, this wouldn't be allowed either, because then we could have a situation where one reference is writing, one reference is reading. This could lead to data races and other kinds of problems. But one interesting thing that we can do in Rust is this. So we can create one reference which is a mutable borrower of Granule. Then we can create another reference which itself is a mutable borrower of that reference that we just created. Now this is totally fine. This pattern is sometimes called reborrowing in Rust parlance. And the reason we're allowed to do this, if you think about the model on the previous slide, is we are kind of passing that capability along. So the full capability gets passed from Granule onto X and then onto Y. So now Granule and X don't have access to that thing anymore. And then those things only regain access when the capability gets passed back along the chain. So at each step, only one reference has access to the value. That's great and all, but how can we use this to represent ownership ideas in a functional type system, like, for example, granules? Well, this is something we're thinking about more recently, so we've actually just submitted a paper about this. So I'm not going to go into too much depth here, I'm just going to quickly go over the ideas. But as we've just seen, linear types can be generalized to allow for quantitative restrictions. So for example, if I have 3 of something, that's bang 3A in sort of bounded linear logic language, we can use one of those things and then we have 2 left. This is just like bounded linear logic. By the same token, uniqueness types can be generalized to allow for what we're calling fractional guarantees. So, just to see how that works, if I have unique access to something, I can borrow that thing. So we have this new borrowing modality, which has a grade that comes along with it. Here, this grade is 1, which means we have the full capability, just like you saw on the other slide. So we're allowed to mutate that thing. But I can then split this thing up, right? So I can split this up into multiple borrowers, but the capability splits up along with it. So I now have 2 halves, which means we're not allowed to mutate, but we are allowed to read from this thing. Now, if you think about how reborrowing should work, hopefully that should be quite clear, we can split this thing up as many times as we like. So the fraction gets smaller and smaller. And we only have unique ownership when all these things come back together. Now, if this looks similar to something you've seen when you've been reading around, then it probably does. This is similar to ideas from fractional permissions, usually seen in a kind of more imperative setting. But it works really well in this kind of graded functional setup as well. So that's pretty much the end of the main body of the talk. There's just a couple of things I want to briefly mention as other applications of these ideas that we've been thinking about. I'm not going to go into much detail at all about either of these things, but I just want to briefly mention them. So first of all, communication. If you hear linear types and communication, you probably think, if you're similarly read to me, of session types. Session types and linear types are really closely related because communication is kind of an inherently linear behavior of these channels. You can't duplicate the channel, you can't discard the channel. It turns out, just like you can generalize linear types to graded types, you can generalize session types to graded session types, and this lets you represent nonlinear communication behaviors, like reusing a channel or having a server that communicates with multiple clients and so on. So that's cool. The other one is security. So it turns out that just like there's a duality between linear types and uniqueness types, There's a similar duality that exists in information flow security. We have confidential data, which is never going to be leaked in the future. So let's say that I have, for example, a secret cake recipe that I don't want to get out to the outside world. Well, we have a setup of grades in Granule that lets us do that. There's a semi-ring with security levels, and it stops us from going from private to public. But there's also the notion of data that has integrity. So this is data that has never been leaked in the past. If my friend goes and leaks my cake recipe to the world, I don't want them to come to me and tell me, I've shown your cake recipe to everyone, sorry about that. But actually it's still secret. We can't let them do that. So yeah, so there are these two kind of different concepts here, but the duality is that one guarantees the future and one guarantees the past, very similar to what we have with linear and unique types. So it's just cool that we have kind of uncovered this more general structure here, and this is something we're exploring a lot more at the moment, what other applications there are for this. So that's basically it. There's my Twitter handle, it's 2023, so there's my Mastodon handle as well, and I also have a website where you can read all my papers and so on. Just a very quick summary. Linearity is about the future, uniqueness is about the past. So similar, but there are important differences between these things. Quantitative types generalize linear types. They'll let us be more precise in the things that we're saying. So we can write more precise restrictions into our types. Ownership, on the other hand, is more of a generalization of uniqueness. So it lets us be more flexible and use something non-uniquely as long as we know we're going to get back that ownership later on. And finally, we have this framework of braided types that we've seen. Powerful, expressive, getting more and more expansive every year, and able to generalize all of these concepts into a single system. Thank you.